Hi, hope you are well. Welcome to the video on integrating logarithmic functions. In the previous video, we developed the techniques with which we could differentiate various formats of logarithmic functions. We established in that context the relationship that if y was equal to log x to the base e, then dy dx is equal to 1 over x. Now we will use that relationship in reverse for integration. So using that statement, we can say that the basic form of integration for log functions will be that the integral of dx over x is equal to log x to the base e plus c. The x from the denominator comes up to follow the logarithm statement in the integration. So if we have the integral of dx over 2x plus 1, then that integral becomes rewrite the log e, and then the 2x plus 1 follows that, and then we divide by the derivative of what's inside the brackets. So it's log 2x plus 1 to the base e divided by 2 plus c, which we can rewrite if we wanted to with log 2x plus 1 to the base e all over 2 plus c. If we have the integral of dx over 42 minus 3x, then the 42 minus 3x comes up and follows the log, so we have log 42 minus 3x to the base e divided by the derivative of what's inside the brackets, which is minus 3 plus c, and we can rewrite that as minus log 42 minus 3x to the base e over 3 plus c. Now, to keep your attention on the integrating task, say to yourself, time after time after time, the integral of 1 over an x term is log of that term divided by the derivative. If you say that, you'll keep your concentration and you won't make errors. Note that unlike for ordinary integration and differentiation, we are not changing the values of any indices here. We're just writing down whatever's in that denominator. Now, I'm not going to have to worry about this, but the substitutions for definite integrals are always the same as previously. It's the way in which we get to the integral that is a concern at this time. So the technique that I've outlined there is pretty much what you're going to use all the time. But we need to make a few observations on the characteristics of the fraction which integrates to a log. The first is that the term in the denominator does not have an index. It's always a 1. So the integral of dx over x squared plus 1, the term in the denominator has a square in it. So immediately we can say that is not going to be a logarithmic integration, it's going to be something different. The second characteristic of the fraction which we're looking at to integrate is that there are no brackets raised to a power. If there are brackets, then they would be to a 1, but there's not, for example, the integral of dx over bracket x plus 1 all cubed. Anything like that is not a log. It doesn't integrate to a logarithm. A third characteristic of the fraction that we're interested in is that there is no x term in the numerator. There can only ever be a number. So here our example says the integral of 3x dx over x plus 1. Yes, the x plus 1 in the denominator is fine, but we can't have the x in the numerator. So consequently, that integral is not going to go to a logarithmic function. Okay, now we can look at some considerations to help us make our integration of logarithms successful. First of all, the constant terms that are included in the thing that we have to integrate. Always leave the constant where it is. So if we have the integral of 4 dx over x, leave the constant in the numerator. The integral then becomes 4 times ln x plus c. If we have the constant in the denominator, for example, integral of dx over 4x, leave the constant in the denominator, don't bring it up. The integral then becomes a quarter ln x plus c. Easy, stick to the rules. The next consideration is when we have one term in the denominator of what we have to integrate. Just because there's an x down the bottom doesn't mean that it's automatically going to be a log. If in this case we always divide each term in the numerator by the single term in the denominator. So if we have the integral of 2x cubed plus x plus 5 over the single term of x squared, then we are going to integrate the terms separately. So it's 2x cubed over x squared, which is 2x, plus x over x squared. Now that does become a 1 over x, and therefore it's familiar. We're going to have a log out of that one. And then the last one is 5 over x squared, which we can write as 5 times x to the minus 2. So now we can do our integration. The integral of 2x is simply x squared. The integral of 1 over x is our log x, our new found friend. And the integral of 5x to the minus 2 is going to be 5x to the minus 1 over minus 1, which is minus 5x to the minus 1, and then our integration constant plus c. Our third consideration is where we have a term in brackets, and inside the brackets there's a fraction of 1 over x. That's probably not going to be a log, although it may involve a log. So what we do always is to expand the brackets first. For example, if we have the integral of x plus 1 over x all squared, don't be fooled by the 1 over x inside. If we expand these brackets, we'll have x squared plus 2 plus 1 over x squared. In other words, we will not have a 1 over x term after the expansion. So clearly, no log term is produced by the integration. But if we have the integral of x plus 1 over x squared all squared, and we expand that, we're going to have x squared plus 2 over x plus 1 over x to the fourth. Now the middle term there, which is 2 over x, does have the fraction that we're after the expansion, so therefore the integration of that term will produce a log term. The others obviously will not. The fourth and last consideration is that we have many questions with log integration which involves the reverse chain rule. Such a question would be of the form the integral of x dx over x squared plus 1, or the integral of e to the x over 1 plus x dx. Now, both of these expressions have a term which, when differentiated, produces the other term. For example, the derivative of x squared plus 1, when we differentiate that, it becomes 2x. So we've really got a 2x in the top, which we can remove the 2 from. The integral of 1 plus e to the x differentiates to e to the x dx, which is the term we've got on the top. Now, these are the characteristics of the reverse chain rule. We've dealt with that elsewhere, so see either the main logarithmic page for a hyperlink, or go to the index under R for details of the reverse chain rule. Just by the way, these two integrals become respectively a half ln x squared plus 1 plus c and ln e to the x plus 1 plus c. So they certainly produce the logs. Not that the reverse chain rule always produces logs, but here they did. So be careful, follow that one up. Now, most of the integration questions you encounter here involve the usual fractions, but a different type of question, which is fairly common now, asks for the area under a log curve. All of these questions are generally the same, except for the numbers used, of course. As it is not possible with our present techniques to integrate a logarithm function directly, we approach the solution in a roundabout way. A typical question is as follows. In the diagram, the shaded region is bounded by the curve y equals log x minus 2 to the base e, the x-axis, and the line x equals 7. The question is, find the exact value of the shaded region. Now, a difficulty. If we approach the question in the usual way, we would write the area statement as the integral from 3 to 7 under the curve log x minus 2 to the base e dx. But we do not yet have the technique of integrating a log function. We can only differentiate a log function. So to answer the question, we must take an indirect path. We will instead find the area of the rectangle and subtract the area between the curve and the x-axis. So let's do it. The area of the rectangle is 7 log 5, 7 being the distance along the x-axis and log 5 being the distance up the y-axis. Now, as is our usual custom for doing these sorts of things, we draw the slice from the y-axis and write the area statement down as x dy, which is the area of our little slice, integrated from 0 to ln 5. To obtain an equation with x as the subject so that we can put it into that area statement, then we can write our original equation y equals log x minus 2 to the base e. So taking the log form into the exponential form, we bring our e across to the other side, so it's e to the y plus 2 is equal to x. So now we can do our area, which is going to be the integral from 0 to log 5 of 2 plus e to the y dy, just by substituting into our original statement. Integrate, integral of 2 is 2y, plus integral of e to the y is e to the y. We put our limits in. Substitute, firstly the log 5, so it's 2 log 5 plus e to the log 5 minus, substituting the 0 in, the first term disappears, 2 times 0, plus e to the 0, which is always 1. Now, the e to the log 5, remember, it has an e as the main base, and ln has a base of e, so they sort of cancel out to give us a 5, which we've done previously. So we have 2 ln 5 plus 5 minus 1, which is going to be 4 plus 2 ln 5. Just finishing by going back to our original concept of our approach to this question, we're going to find the area is equal to the area of the rectangle, 7 ln 5, minus the area we just calculated, which is 4 plus 2 ln 5. We simplify that by the log 5s reducing, so we have 5 ln 5 minus 4 units squared. These are reasonably common questions, so make sure that you follow this logic very carefully. There's a couple of other questions in the Test Yourself series, so get into those. Important to be able to do this one and know what you're doing. So in summary of our discussion, if we are required to integrate an expression of the form y equals 1 over x, then we say the integral of 1 over x is log x to the base e plus c. When we have a number in front of the x, then we add to that comment, divide by the derivative. It is important to always look at the structure of the given expression to determine any special characteristics that it may have, which might impinge on the way in which we write the logarithm. Good luck. Hope it goes well. Test Yourself 1 is awaiting you. Go and do it. Hope it goes well. Bye.